So on behalf of Josie Alla, who is the convener of the Friday seminars, who is overseas at a conference, I'd just like to welcome you all, and glad that you're all here. Just quickly, I'll introduce our distinguished guest. This is Jeffrey Freedman, who is an atmospheric scientist at the, as you can see on the screen there, the Atmospheric Sciences Research Center at Albany, which is actually a sister organization to our own school here. We used to be called the Marine Sciences Research Center. And a number of these research centers were set up in the state in the early days. So Jeff collaborates actively with Brian Colley and students here at Stony Brook, and Brian could not be here today, otherwise he'd be doing the honors to introduce Jeff. But very briefly, Jeff is Brooklyn bred, born and bred, and as I say, you might take a boy out of Brooklyn, but you can't take the Brooklyn out of a boy. So Jeff got his first degree in meteorology and oceanography at Brooklyn Polytech, and it's now called the Tandon School of Engineering of NYU. And then he went on to law school. And I must say, you're the first atmospheric scientist, Jeff, that I've met who is also a lawyer, so I better be careful what I say. Jeff has an MS and a PhD in atmospheric sciences, both from SUNY Albany, and has been in private business for himself, promoting atmospheric sciences. His main research focus, reading from Jeff's website, is on renewable energy and atmospheric boundary layer processes. He'll explain what that means. This includes work on improving wind and solar power production, forecasting, outage prediction, that's when the power goes off, modeling, developing instrumentation, improving modeling approaches for offshore wind energy, which he's going to talk about as well today, and use modeling and observations to better understand weather and climate influence. And he has some very innovative instruments. One's called LIDAR, which is called, I think, what is it, light detection and ranging, which is a way of very accurately looking down from an airplane, mapping the topography of the land, but also looking up, if you can detect rainfall. Jeff has published a huge number of publications. He's now speaking from the Adirondack, Lake George in upstate New York, although that's not really where he is.
No.
So Jeff, welcome to Stony Brook again, and I'll hand it over to you. Thank you.
Thank you, Malcolm, and welcome everybody. Thank you for being here this afternoon. As Malcolm mentioned, I'm a research faculty at the Atmospheric Sciences Research Center up here at the University of Albany, in Albany, New York. And I've been here for quite I guess 9 years now. So, and yes, I have sort of this circuitous career, starting out as a lawyer, working for the New York City Department of Environmental Protection for several years as an assistant counsel there. And then I went back to school and pursued what I really wanted to do eventually, which was atmospheric sciences. And that has taken me also on a long journey, doing lots of different things. So, and this talk actually originates from something that Malcolm had found. I had given a talk, and Malcolm and I had actually had some interactions a few years ago on Hurricane Sandy and some other issues along the Northeast coast. And this is a talk I actually gave at an offshore wind conference in 2014. Part of this is, and the reason is because the offshore wind energy industry was beginning to get going in the East Coast, and especially with at that point the construction, and then later deployment of the first offshore wind farm in New York and Block Island, deep water wind. So when I was at AWS True Power, we were heavily involved in that. And it got me to thinking, it's like, well, when you're doing offshore wind, in other words, when you are planning, you have to take into account not only what the wind environment is and what the wind resource is, but now you have to take into account what's going on below the sea surface down to the seafloor, and that air-sea interaction component comes into play. And Sandy comes along, and I said, you know what? All this designing that we're doing is based on 50 and 100-year return periods from the data that we had prior to Sandy. So I was curious, what did Sandy do? You know, is Sandy one of these storms that's just a blip? Has Sandy affected these return periods? And so I took a little dive into that. And so I'm going to present some of that. And I have some information also on offshore wind we'll get to. So in essence, Sandy came along. There was an assumption in the offshore wind community that I kind of detected from conversations that it was not a particularly strong storm and would have had minimal impact on offshore wind facilities. And that may or may not be true, but from my perspective, it's not necessarily true. So a little bit of background on Sandy here. Some of you may have been younger. Well, everybody was younger, but some of you may or may not recall what kind of a storm Sandy was. It was a hurricane, Category 1 storm that was transitioning to an extratropical cyclone as it approached the East Coast. And it took a really odd path. And I'll show later on that it's an odd path, but not unprecedented in our lifetimes. So here's some reports that from the National Hurricane Center that they put out after Sandy. You can see how large the pressure field is, those lines colored cyan there. Very deep storm. Now it's barely a Category 1 storm, but a typical storm with a 943 pressure would be a Category 3 hurricane. But since it was undergoing extratropical transition, wind field expands tremendously. So you may not have those 120, 130 mile an hour winds, but you have a broad area of near hurricane force winds. And during all this time, when Sandy was approaching, my cousin lives in Long Beach, Long Island, and he was really concerned. He was 2 blocks from the ocean, so we had some texts going on. And you could see during this, I told him, yeah, I think you could make it because you're about 12, 13 feet above sea level where you are. And it turned out that the water did come within a few inches of where he had a generator that was powered by natural gas, which if that gets flooded, leads to some really bad things happening. Now, the other thing that's unusual about this storm is that the strongest winds, as I said, strongest winds for the hurricane, a warm core system, as we would call it, tend to be around that eye. Well, in this particular case, it's not necessarily true anymore. As storms undergo this transition, lots of different things happen, including that wind field expanding and sometimes those highest winds being to the north, wherever the pressure gradient is tightest. But then I'll get into something else in terms of, well, do those winds actually get to the surface? And that has to do with atmospheric stability. So this is a really complex interaction going on between the atmosphere and different parts of the atmosphere, the surface up to 10,000 meters at least, and then what's going on along the coast. So, as I said, the highest sustained winds occurred well to the north of the storm, and they came in 2 phases, and I'll show that as well. That transition happens hours before landfall. This led to an expansion, a huge expansion of the wind field, but it also led to some confusion because at the time, the National Hurricane Center had a policy that, well, once it's extratropical, we don't deal with this anymore. And so now it's up to the local National Weather Service's offices to deal with it in terms of a regular extratropical storm. Well, it was total confusion in that sense because you have hurricane warnings and it's like, oh, no, now it's something else. And so that policy had to be changed because of Sandy, but that's another story. As I said, those tropical storm force winds covered an area of almost 1.5 million kilometers and covered, in other words, 1,500 kilometers from basically from south to north. And the areas that were experiencing, pretty decent seas, 12-foot seas, 4-meter seas, was covering about 1% of the Earth's ocean surface. And it looks kind of like that. So these are, this is analysis from the Ocean Center showing what was going on right around October 29th. You could see 12-foot seas are just covering pretty much the entire Western Atlantic from Florida north to the Canadian Maritimes. So here's that unusual track again. This is the best track estimates from the National Hurricane Center. You could see it transitions between 1800 UTC and 2100 UTC on the 29th. So it's actually transitioning when it gets onto the continental shelf, which may or may not have something to do with what's going on. That's a little beyond what I would know. I've circled a couple of places that we're going to look at in terms of analysis. So a couple of buoys out there, 44009, 44025, that one south of Fire Island, and then some analysis from where Ambrose Light used to be, and now buoy 44065. But you see the problem we have is there's so few offshore observations. With offshore wind power coming into play, we'll have more observations, but that opens up another story in terms of what is proprietary and what's not. I'm not going to get into that. The other problem is most of those observations are just less than or 5 meters or less. So you really don't have any idea what's going on above that surface. Here are the highest gusts. Essentially, this is from the New York Weather Service Forecast Office, and you could see essentially you have hurricane force gusts everywhere from New Jersey out to covering their entire region, forecast office area. And there were hurricane force gusts into New England. Actually, as it turns out, if you look at this lower table, hurricane force gusts extended from Michigan to the East Coast. That's how large this wind field was. And you can see there were all-time low pressure records set in the upper table there. And some of these records, some of these stations have records going back into the 19th century. So this was a storm for the ages, so to speak. Storm surge, as you can see here, was the biggest storm surge was reported in the New York Harbor area. And I'm sure you all well know why that is. You have a strong easterly fetch over several tide cycles. The water tends to pile up. Now you also have a southeasterly fetch going on as the storm is approaching as well. And so water has nowhere to go in Long Island Sound, down through the East River and down from the Hudson River into New York Harbor. And there's the tidal gauge at the battery. And you could see it reached nearly 14 feet, which was 2 feet above any record of any history. I think I was looking back, there was an 1821 hurricane that even which probably was the all-time record up to that point, although the measurements that back then, of course, don't really exist. Now, precipitation was rather unusual. People think of a hurricane or a tropical cyclone and, oh, we're going to get pelted with a lot of rain. And the forecast for the New York City region and Long Island was, yeah, we're going to get 3 to 5 inches of rain. Well, that turned out not to be the case. Most stations on Long Island or New York City reported less than an inch of precipitation of rainfall. And that's simply because when you have landfalling, transitioning tropical cyclones, you tend to get the heaviest precipitation in the left front quadrant. Usually, if you have a storm moving from south to north, that would be to the north and the west. Well, in this case, you have to change your orientation. And if you can see, yeah, in that left front quadrant, right, based on this track, yeah, the South Jersey, Delaware, the Delmarva Peninsula got hammered through precipitation, but there's nothing here. And that has to do with how the system transitions. So very, very rare track, not unprecedented in a sense, and that led to this kind of weird distribution of precipitation. Another thing that was unusual is that, remember, this is happening in late October. And so there, parts of West Virginia got nearly 3 feet of snow. So it was the first time we saw blizzard warnings simultaneously with hurricane warnings. I've never seen anything like that with one storm. So this was, again, one for the ages. And this is just a radar that shows you how the precipitation distribution comes. You can see these bands coming in. Here comes the center now. It's going to come across New Jersey, but the bands are essentially doing what any hurricane would do. It's just that quadrant as you're transitioning. So you can see the heaviest precipitation moving across Delaware into Maryland, and then it's beyond the range of this particular radar, which is out of Philadelphia. But you could see how West Virginia would have gotten 3 feet of snow. Many of you may or may not recall some of the damage that was done. It was quite amazing to see this. So this is also from that some certain reports that were then excerpted into that National Hurricane Center report. You could see the famous roller coaster off of in New Jersey was basically destroyed. You could see the flooding in the subway in the upper right. Lower left is lower Manhattan, Lower East Side, and then the water just rushing into the subway stations at different places. Quite amazing. And then I took a trip down there. Again, I have a family down there. So my mom lives in Brooklyn. My cousins are in Long Beach. They had no power. They had no water. So I brought a lot of water in 5-gallon jugs to my cousin he was staying there. His family had been evacuated, but they really needed the water. The other thing I noticed driving around is, and this is Manhattan Beach and Brooklyn, was incredible amounts of sand that were deposited in the streets. So the beaches weren't washed away; they were just kind of washed onto the where people lived. And so you could see that. Restaurants were damaged. There's a restaurant I used to go to in Sheepshead Bay all the time, a really good Turkish restaurant, and he had catastrophic flooding there. It took him months to reopen. So it really had a tremendous effect on people, and people were angry because they felt like they weren't nobody was coming out to help them. But you can imagine this kind of widespread damage is difficult. So this is Broad Channel. That's an area in Queens, in Jamaica Bay. It's really beautiful. It's the only place where you could take the subway to a wildlife refuge. And then finally, some people did have a sense of humor. And but again, the damage was just incredible, just to go through that and to see what people were having to deal with. Now, this was exceptionally well forecasted. I recall seeing this a week ahead of time. You're an atmospheric scientist, you're checking the models. And I would talk to colleagues and I'm saying, is this real? Is this really going to happen? And if you look on the left, that's the European Center's medium range forecast ensemble envelope. And you could see most of the ensemble members 5 days out had that storm making that left turn into the coast. The GFS back then, the GFS is the global forecast system, as you know, the American model, so to speak, as people call it in the media, did not capture onto this. It had a couple of members that hinted at it. But for the most part, the essentially consensus track had it going out to sea, but that changed. And again, I was, communicating with my cousin about this, 4 days, 5 days out, saying, "Hey, look, you may have to evacuate." And their titles and storm surge forecasts were then coming through, and storm surge forecasts were also quite accurate. I have to say that it was quite amazing to see how well the models dealt with this storm. They were really good at this. Now, for wind, since a big focus of mine is offshore wind, I was interested in like, okay, what kind of wind would you expect in this? And why did we see winds that were so far north? And how do we predict winds in a storm like this? Well, the problem is, when you have a hurricane, National Hurricane Center uses essentially this publication to get an idea of what the winds will be at higher levels, especially because you have a lot of high-rise buildings along the coast. You want to get a good idea. And essentially, they're assuming almost like there's neutral wind shear. In other words, stuff is going to mix down to the surface. And you could see that here. But the problem was, and we'll get to that shear value in a little moment, that's not necessarily the case when you have a storm undergoing extratropical transition. Remember, this is late October, so those sea surface temperatures, they're no longer, very warm. You've got a cold sea surface temperature, right? In the 40s and the 50s in some places. And so the question is, how does it interaction with those cool sea surface temperatures with this hybrid storm environment? What does that do to the wind field? What does that do not only in the horizontal wind field, we've looked at that, but in vertical? And so there's an 80, as you may know, there's an 85-meter tower at the Brookhaven National Laboratory out there. And so I was able to get this data and say, well, let's take a look at what they showed out there. And you could see here, I have the wind speeds at 10, 50, and 85 meters, red dashed, green dotted, and the yellow dot dashed lines. And then I plotted the shear. And the shear in the wind energy industry tend to use a shear exponent alpha. It's based on this particular relationship where you have a measurement height, R, your wind speed is U, and then you can take if you have other measurements at Z, at height Z, you can then derive what the shear exponent is. And that's important for wind energy applications because oftentimes, up until recently, you've had to essentially extrapolate what that wind profile is going to be for a wind turbine, since the rotor planes are now hundreds of meters across, and the rotor tip for the machines that will be going in the offshore waters is going to be 260 meters high. Well, you're not putting a tower out there, and the LiDARs that they had out there, these are the profiling, wind profiling LiDARs, up until recently, only extended up to 200 meters. So if you look at this plot, you can see, well, you've got the winds, ramping up. And you can see they're basically out of the north, northeast, 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 and then you get this little lull as the system. Now remember, the system's 200 kilometers to the south, so it's not like we have an eye coming through here, but something changes. And what's changing here is that shear. The shear is going to be related to the stability. So the stronger the vertical wind shear typically means you have a pretty stable environment at the surface. In other words, from a temperature perspective, it's going to be cold at the surface, okay? And it's very difficult to move high velocity winds down or anything up for that matter. Things tend to be suppressed. But in this case, things changed when the wind shifted to the southeast and the shear environment changed briefly to something negative, which was really odd. But this is also going to affect, then you have a really, really high shear as well too. And so this was really puzzling to me. And so then what's a really great source is the National Hurricane Center sends planes out there, as you know, the hurricane hunters. And they thankfully continue to drop sondes. And so this is a typical drop sonde that they use. It's great data. I was able to get it. I'm going to show it to you shortly. It's very high resolution data. Of course, what happens in hurricanes, things get kind of nutty down towards the surface, but it's meaningful in that particular case. So it's going to give you temperature, humidity, pressure, the components of the wind, and derived values for things like potential temperature and virtual temperature and things like that. And so here are the locations of those drop sondes through time as the storm is approaching, and I've overlaid the map. And we'll take a look at a couple of things. So they had some really great data coming out of the storm as it was approaching the Jersey shore. So this is about a few hours before landfall. But the shear values, and we'll get to that in a moment, go from negative, which means you have essentially decreasing wind, to strongly positive, which means that rapidly increasing the wind speed with height. And we'll look at these particular drop sondes. So this one is down near the Jersey shore in South Jersey, well, more southern Jersey. And you can see the pretty high shear values near the surface. And this is really unusual to see something like this where you have very strong winds, but still a good stability. And you can see that the white dots represent the wind observations, the red dots represent the potential temperature profile. So you can see it's rather stable. In other words, it's increasing with height. And then those winds are strong out of the northeast. So you get this really decent shear near the surface, within 100 meters of the surface. And if we go to another place now, where the SSTs are much higher, so this is further south, you can see you got a different picture, but incredibly strong shear. And so this is hard to explain, but you also have on the right side directional shear. So it's really difficult to figure out what the heck's going on here, other than you can see here the lowest values of the wind are pretty straightforward with this strong stability here, but that stability goes away. So you can see that you have pretty much a neutral to unstable atmosphere, and that's allowing things to mix down pretty rapidly to here, where you're having 40 meter per second plus 40 meter per second winds here just above the surface. And those winds eventually mix down on Long Island, which gives you those gusts to nearly 100 miles an hour at, I think, at Eaton's Neck. And again, another profile right before landfall, right near New York. And again, we still have a more easterly component. You still have some pretty strong shear though, but now that strong shear is a little above the surface as well. So some really odd things were going on as the system was transitioning. So getting on to those extreme winds, what did we see? And now this is a question, right? Remember, we saw those shear values were all over the place and pretty strong shear. And the question is, if you do get those winds mixing down to the surface, what happens? Well, these are numbers from either Ambrose Light or the new buoy, and these represent the maximum winds observed. And now I'm extrapolating up to 90 meters because I'm interested in the wind energy situation. Remember, Ambrose Light at the time was at 29 meters, so it's a different altitude than the buoys 44,025, 44,009, which measure at around 4 meters. So the question is, how do I calculate the sustained wind, U star, which is given by that asterisk, U max, which and the gust, which is important for wind energy applications. And actually it's more related to turbulence intensity, but that's another story. And you could see that if I change those shear values around, those return periods, and I'm using a typical extreme value method, a typical Gumbel distribution to get those extreme values, but you got to be careful with that. And you could see if you change those shear values, well, your return period values are going to be much different. So for example, you're looking at where Ambrose Light used to be a 50-year return using a hurricane return value, given a maximum wind speed of 36 meters per second is 44 meters per second. But if I have a shear value, which is much higher, it gives you a much higher wind speed of 57 meters per second. And then you can go on to the gusts, and you can see where the 100-year return periods can be quite different simply by changing that shear value as you extract. Very, very important issue for wind energy applications, because it's nice to know the wind's at 5 meters. I want to know what's going on at 100, 120, 140 meters. And you can see these are category 4. These return periods would give you basically category Cat 5 wind speeds. Then it was the wave characteristics that we needed to take a look at. The question is, all right, how do we have to deal with the fact that waves are going to be battering the turbine structure, and then you're going to have a possibility of what's going on at the turbine foundations. These are monopole foundations. Some of these are going to be I don't know if they're going to be monopole. Some of these are on quadrupods. In other words, if you look at the deep water wind, they have 4 essentially support structures going down to the surface. So the question then is, all right, I have to deal with any kind of potential scouring, and that obviously is going to be affected by what the waves are doing. So the question is, how do we look at that given the existing data we have here? So you look at it, typically use a Rayleigh distribution, and that gives you this probability function. And then it's like, okay, I can take that and say that, I got the significant wave height, but I want to know what the extreme value is going to be. And I'll just multiply by 1.86 using this. And pre-Sandy, you could see that the values are pretty impressive, and the return periods are pretty impressive, those values. You have 8 meters height at Ambrose, and a 9.3 meter height at 44,025, the buoy south of, I guess, Fire Island. And what you see there, they was actually set, in fact, the Ambrose measurement was set in 2011 during Irene. And the other one was set during the December 92 nor'easter, which I think doesn't get enough publicity. That storm was quite an amazing nor'easter, the December 92 one. So now what happens with Sandy? Well, you've pretty much added 2 meters to what happened at the Ambrose site. Incredibly impressive. You have added a little bit more for the buoy south of Fire Island, but notice the one that's east of, let's say, I think that's southeast of Atlantic City, 44,009 is about 8.1. There wasn't a change there. So the big change is going to happen right near Long Island and near entrance to New York Harbor. And you can see those return period. 10 meter wave at Ambrose Light is quite impressive. Now, you're not going to get those wave heights, those return periods, because the water, I think, is only about about 20 some odd meters deep, but it's quite impressive nevertheless. The one further south, you're going to get that. And that one further south is right where those wind energy areas are. I was just curious about this. I plotted up some stuff last night. I said, well, I got all this long-term data, and let me revise stuff since I did this in 2014. And I'm always curious in trends. So on the left side, you'll see, all right, is there any trend in significant wave heights at these places? So here's an annual median significant wave height at that buoy south of Fire Island. There is a slight increase. I wouldn't call it meaningful, given that pseudo R squared value in terms of the trend, which is very low. But nevertheless, it's indicative of something. It's kind of similar to what we're seeing with wind speeds, a slight increase. And on the right, you could see, you're not going to get I never think, one storm, two storms are going to change everything. So trends really are meaningless in terms of annual maximum significant wave height. You can see in 92 storm, the December 92 storm is up here, and Hurricane Sandy is up here. But the rest of the time, it's, just kind of random. So the question that has come up, Malcolm and I have discussed this, was Sandy really a 1 in 700 year event? And I'm like, well, some people are thinking it is, and there's a reason for that. And the reason for that is there were some articles that came out after it, and well, we're going to throw some, extreme value analysis on this, but here's the problem. Okay. Yes, if you're looking for a storm that's going to track exactly like Sandy did and hit the same spot on landfall, yeah, you could say it's a 1 in 700 year event, but you could say that about anything for that matter. What's the possible, a tornado, anytime you're looking at something that's so constrained, it's going to be at a very, very rare event. The problem is it doesn't have to do exactly what Sandy did in terms of its track. And if you look at what I've underlined and the approach angle, to cause a lot of damage and to cause a lot of havoc. So to me, this kind of thing is almost meaningless. And the reason for that is, well, number one, why did Sandy do what it did? And so for your atmospheric science folks, these are 500 millibar geopotential heights. Essentially, this is what the upper atmosphere is, how it steers things, right? And so it's been superimposed. This is an analysis, I think it was done by the Hurricane Center. And so this is essentially, all right, here's what was going on. And so the colors represent the anomalies in the heights. So you can see, and they're in standard deviations. So you can see you're pretty much at 3 standard deviations for that anomalous high over Greenland over here. Actually, this is incidentally a setup that gives you nice blizzards along the East Coast. And so what you got going on here is, well, Sandy has nowhere to go. And so sure, it's going to get steered up here, right? And then, well, I got to make a left turn because that's essentially the way I have to go. As you go through time, you can see how these searing currents from this high, upper level high over the Canadian Maritimes are essentially forcing Sandy to take that weird left turn. Nevertheless, if you remember, the models saw this happening days in advance. So this is not so anomalous that we couldn't predict it 120 hours ahead of time. And so as it turns out, we've had hurricanes do this in the last 80 years or 90 years or so. All right. And that have affected the northeastern US. And I have here essentially tracks from 3 of them. Sandy is the red hurricane symbol, but you have the 38 New England hurricane, which everybody there should be very familiar with. If you're not, then you should get yourself familiar with that storm. And of course, and then Hurricane Hazel. Now, Hurricane Hazel was interesting because it transitioned to an extratropical storm and still had hurricane force winds up in Toronto. So you had a very similar, in fact, the highest wind speed ever recorded in New York City was associated with Hurricane Hazel. It was 113 mile-an-hour gust at the Battery. Now, back then, the weather station at the Battery was at 400 feet above sea level on a building. Nevertheless, it's still recognized as such. And so these are just, 3 situations where you have a storm, hurricane that's going to come up, and instead of recurving out to sea, which they tend to do, is going to veer to the left, is going to veer to the west. All these tracks veered to the west at one point. The question is, they're all not doing it at the same place, but they're doing it. In other words, it does happen. And, I've listed here some other notable storms that have done quite a bit of damage or could have done quite a bit of damage. So the December nor'easter is the March 1962 Ash Wednesday storm really did tremendous amount of damage to Jersey Shore. Again, it was a storm that was captured and slowed down and just kept going on and on and on. December 92, the same story. It's kept several tidal cycles. Upper level pattern basically forced it to a standstill just south and east of New York City. Hurricane Gloria, that was a more classic hurricane approach to Long Island. caused a lot of power outages out there. Blizzard of 1978, another storm that got captured and lingered along the New England coast. You had 4 feet of snow in Rhode Island, a huge amount of tidal flooding in New England. Some of the record highest tides ever set were in that storm out there. Perfect storm of October 1991. I actually drove through Broad Channel, or tried to, because it was underwater during that. Although there was no precipitation here, it was actually not a bad day. It was just a huge storm. And then Hurricane Irene, of course, which also had a very, very large wind field. So Sandy was essentially the catalyst with Irene for the development and operation of what we have now, the New York State Mesonet. So I'll get into that in a moment. In other words, the governor at the time, Governor Cuomo, and the feds, actually at that time was Vice President Biden, got together and decided that they were going to provide $30 million as a supplemental Sandy funding for the New York State to set up a network, which is quite a valuable thing. It's been in operation for a bit now. And again, this is a big issue for offshore wind. Now, we have to deal with this, but utilities, developers, you know, ISOs are independent system operators. In New York, we have the New York Independent System Operator. New England has one. Other operators of wind farms, federal state agencies, everybody's aware of this. And so basically, you are designing offshore wind facilities to deal with these kinds of situations. Well, I hope they are, but they should be. And so I'm going to segue a little bit into that. Malcolm asked me to talk about what's going on in offshore wind. And so I'm doing some work with Brian Colley to develop, and I'd like to thank him for actually getting me, Malcolm and I together, and then this talk, as it turns out, are working on this flux system. But I'm going to have better forecasts for this region. But I'm going to talk a little bit about what's going on. This is a picture of that Deepwater Wind Rock operating wind farm. Hopefully some of you have gotten out there. These are 6 megawatt wind turbines, GE wind turbines. There are 5 of them, so they're supplying 30 megawatts of power when they're at capacity. In fact, Block Island shut off their diesel generators for the first time in 100 years when these turbines went online, and so their power comes from here, pretty much, for the most part. What's going on with offshore wind? A lot. There was a auction for leases. These leases here, south and east of Long Island, east of New Jersey. 6 wind energy development areas, about 500,000 acres. There were 64 rounds of bidding, $4.37 billion in bids just for the right to develop. So now, and these are the companies on the right. But we still have a lot of gaps in understanding of what's going on. And so part of the work Brian and I are doing is trying to fill in those gaps in terms of better forecasting. So you think of renewable energy as weather driving energy generation. Just some more background as to what's driving offshore wind in New York State. We do have and this is where I put on a little bit of my legal hat, I guess. The Climate Leadership and Community Protection Act, that became law in 2019. And the state is targeted to become carbon neutral by 2050, and 100% of all power generation in the state has to be from renewables by 2040. And that's going to include, you see the goal here of 9,000 megawatts by 2035. That's going to be upped, I imagine. We're pretty much ahead of that. Right now, we get 25% of our generation from renewables, but 80% of that's from hydropower. So pretty much everything is going to have to come from wind and solar from here on in. And right now we're at about 9 or 10% of our generations from wind and about 5 or 6% from solar. And so those are going to be rapidly changing over time. I mentioned the Mesonet. The reason I did that is we designed it somewhat also to take into account when we put in the application to FEMA was like, well, renewables have to be part of this equation as well. It was essentially developed as an early alert system for weather, and but it's also to be used for other applications, including energy and renewables. And you can see on Long Island, we do have these LIDARs, and actually they're thermodynamic profiles too. We have microwave radiometers at 6 sites, including one at Stony Brook. So, and then one at East Hampton campus, I think, of Stony Brook, and then Wantaw, which I'll focus on in a moment. So over there. So they're the new generation. I think we're going to be hitting 12,000 megawatts in the next 15 years. They're the offshore wind areas. There's the station actually at Wantagh. It's on a sewage treatment plant there. And so we have the LiDAR here in the middle, microwave radiometer over here. It looks like a big mailbox. And we do have a sky camera there. I don't know where it is though. And then the standard site does give you temperature, humidity, wind, pressure, precip, irradiance, soil temperature, and moisture as well. Wind energy, the mesonet value is resource assessment, forecasting. This is something that Brian and I are working on, and plant performance, of course. I have a student, Elizabeth McCabe. She submitted a paper based on a master's thesis on some work she did using the existing networks out there. So you can see on the left, we have New York State mesonet sites, the green, ASAW stations are the yellow. Those are the ones that are usually at airports. We're using the buoy data in blue, and then New York State Energy Research and Development Authority has deployed 2 buoy-based LiDAR systems. You can see in the red dots here in the lower left at the Hudson North, and this is Hudson Central here, wind energy development area. So we did a little bit of a study, and we found that we do get, and this is work that actually Brian had done back in 2010. I'd actually done it when I was in the private sector also, that there is this low-level jet in the New York Bight that comes right on shore in Western Long Island. Problem is on the right, you could see that you can get some really high, pretty decent winds, but and that jet nose is right in the middle of that rotor plane, which is indicated by the wind turbine there. And so the winds do increase rapidly, so you have very strong shear. And this is something that we have to take into account. So the Wantagh is in green there, the green diamonds, and then the 2 buoys are the red circles and black circles. You can see they track this pretty well. Elizabeth identified about 50 low-level jet events over a 3-year period. She developed an algorithm which is now available on the mesonet, which does a little diagnostic test and a little bit of forecasting to identify sea breezes and low-level jets. And you can see on the right, this is the wind profile. And for the most part, all the jet maxima, that low-level jet maxima is usually around 150 meters, right in the middle of that rotor plane. And it can be quite strong. This is a good thing for the most part, but you have to take into account when you have that kind of shear across the rotor plane, there is going to be an effect on operations and maintenance over time. So that has to be taken into consideration. But it does increase those capacity factors. In other words, the output from the machine as compared with the nameplate capacity. Typically offshore, you have about 45 to 50% capacity factor, which means if you have a turbine that's rated at 10 megawatts, it's going to, on an annual basis, produce about 5 megawatts per every hour of the year. But in this case, you're going to be capacity factors are going to be at 100%. The climatology, not surprising to everybody here, the frequency of sea breeze days is going to be in the middle of the summer, July, and the low-level jet essentially accompanies it. So we know that it's connected. So the idea is to get behind the physics. So this is something that we're studying now as well, that Brian and I are looking at the physics of this low-level jet and the sea breeze and how we can better forecast it using numerical weather prediction. The great thing about it, it matches your load. So this is the demand of electricity, well, the load of electricity. Demand could be a little different, but for the most part, they're going to follow the same curve. So the load from New York City is that black solid line, and it's pretty smooth. You could see it has a dip in the morning right before people wake up. And then people wake up and then the load goes up. This is a classic sea breeze day, it turns out. But you can see how the wind speeds at the 2 buoys offshore match pretty well what that load is, which means offshore wind is going to go a long way to keeping energy cheap on Long Island and New York City, because, you know, even if you have 100% renewables, the wind resource is going to be really good on those hot days. And you'll also have solar as well, because usually on a hot day, it's sunny. And now I'm going to just go back in time, a little history. I was involved when I was at AWS True Power with the first DOE offshore wind research project in this part of the world. We put instruments on Ambrose Light, and we'll get into that in a moment. And we also had instruments at Fort Tilden in Rockaway, just to get an idea of the wind environment. And you can see on the right, we're installing, you know, a bunch of instruments. flux measurements, more wind instruments, and on the upper right, you could see a SODAR. So we used SODAR at the time. It's much cheaper than LiDAR, but I'll show you that's not necessarily the best thing. So this is what you ended up with when we installed everything. And you could see that's where the SODAR is. You could see that we had heat and momentum fluxes and some additional measurements. The problem, and then we had a companion station at Fort Tilden, which is about 9 miles due north, right? And we had another SODAR, and we put a tilt-up tower there. And we also had a buoy, which disappeared after 2 months. So no one knows. What happened to Ambrose? Well, you know, it got hit in an collision with a tanker, and it's no longer there. That's sad. So there is a buoy there now. We did get some measurements, so we have a report out here that was published back in 2007, and that gave us some insight in terms of, you know, we can use similarity theory, Money-Novikov similarity theory, and Businger-Dyer. These are relationships in the atmosphere that get you the wind profile from flux measurements, or vice versa, let's say. And if you look at the Western sector, because I decided that was the cleanest data set to use, not surprisingly, with a flow, offshore flow, you don't get stable conditions very often, unstable more often, and neutral for the most part, because you do get some kind of air mass modification as you pass over the water. And you can see it actually worked out pretty well. And then if I just took a particular day on a very stable day, you could see that, so the neutral line there is that straight black line tilted up to the right. That dotted green line represents, using those relationships, what you would expect the wind profile to be using the flux measurements you have under stable conditions. And the open circles represent what the SODAR was seeing. So we actually did pretty well there, and I was pretty happy with that. Unfortunately, the cormorants loved Ambrose, and they didn't care about the SODAR chirping away, and they didn't care about the foghorn going off. And so we ended up in the lower right with a malfunctioning instrument because of guano just frying the motherboard. Anyway, I'll take us to a conclusion now. About Sandy, the aerial wind and wave states were basically the worst conditions experienced in the northern mid-Atlantic in the last 50+ years. Again, I can't say that the last 700 years, we can't. You know, who could say that? There's so few measurements out there, and we've had so many storms. Are there going to be more frequent Sandy type storms in the future? That's possible, and that's a climate change issue. And I'll just say briefly that you can have situations, because we do see this where there's more blocking going on in the upper atmosphere. In other words, we have more meridional flow than a traditional zonal flow that you get. So when you have that kind of situation, you open up the opportunity for more storms like this, those storms that make a left turn towards the coast or move towards the north or northwest rather than recurving out to the east. Extreme value analysis gives you a large range of return periods. That's going to be dependent upon the shear, very important. And of course, the method you use in your extreme values analysis, I can't emphasize that enough. The dropsondes that we saw, you know, it showed a large range of shear. So, and again, Sandy was the catalyst for the development and deployment and operation of that measurement, and I implore you to take advantage of the data sets that we are developing there. So the question is, are we ready for another Sandy-like storm? This is something Malcolm touched upon. I think it really depends upon where you are. I think if you're in a community that's well served, you're going to be better prepared. If you're in underserved communities, underrepresented communities, again, it's the same thing. You're much more susceptible to storms like this. You still are to this day, along with the other extreme weather that's coming with climate change. So, you know, something Malcolm and I have been talking about. This is actually, I took this picture back in June 2004, not realizing that, oh, you know what, this is a place that could be interesting. You know, I always wondered about this as a kid growing up in Brooklyn. You could see these places and say, oh, that's kind of neat. from Gravesend Bay in Bensonhurst and Bay Ridge. So when we were going out there, I said, I wonder what that is. And now I know. So I'm going to thank everybody. I guess I could take questions at this point.
Well, thank you, Jeff, for this very interesting talk. If I could just make a quick comment about this 1 in 700-year prediction. Interested to hear what you say, because this number thing was generated by throwing thousands of what we call synthetic storms at the New York area. In other words, creating man-made hurricanes in the computer, and then doing this thousands of times, and then saying, well, we only get that kind of 14-foot surge at the battery once in every 700 years. But I think, and I have to read it again the paper more carefully, that there was a fundamental flaw, and that was they didn't take into account the 6-foot rise and fall of the tides. It so happened when that night Sandy struck, it happened to be high tide at the battery. And what's more, the moon was full that night, so it was a spring tide. And so the surge was on top of that. And if the storm had have occurred 6 hours earlier or 6 hours later at low tide, the water would have been 7 feet lower, and it wouldn't have been much anywhere near the damage. So I think this 700 years keeps popping up, and they say, Malcolm, stop worrying about this. Just go home and enjoy life. But I don't believe it. So anyway, thank you very much. And can these huge blades, can they be what they would call an airplane? Can the blades be feathered so they would withstand a hurricane smashing into it?
Right. So the turbines are designed to feather down whenever the wind speed exceeds the cutout speed, which is typically 25 meters per second.
Yeah.
So once you get above that, and that happens 1 or 2% of the time, maybe it depends. These are sustained winds over a 10-minute period. That happens. So they're designed for that. So you say, all right, we got to feather these things down. So they are designed to withstand that kind of weather. Yes. Okay.
So thank you, Jeff. Let's open this up. Just unmute yourself and yell out if you want to ask a question. So some of these turbines differ in federal waters. I mean, the New York State goes out 3 miles, right?
Yes. So 3 nautical miles.
Federal waters go out to 12 miles, and then it's international waters. So how does that affect the research? How does it affect the permitting? Getting the feds involved, does that make it more complicated, or does that provide a great source of new funding?
So what happened, you have federal, there's territorial waters, and then there's an economic zone. So there is jurisdiction over pretty much the continental shelf for, in this particular case, it's Bureau of Ocean Energy Management. It used to be the Mineral Management Service, and then that got reformed when renewable energy came into play with the Energy Act 2005. So before that, it was kind of like the Wild Wild West. We actually had to develop a legal and regulatory roadmap for a Long Island Power Authority project south of Jones Beach, which didn't go anywhere, and the Cape Wind project. And then the Army Corps of Engineers had jurisdiction, simply because any kind of drilling or stuff on the outer continental shelf they had to be involved in. But now everything is reorganized. And so the Bureau of Ocean Energy Management has jurisdiction. So I mentioned the leases, they're well beyond 12 miles. Some of these leases are well out there, way out there beyond 12 miles. And as you saw, there are lease auctions. It's very similar to what you have for oil and gas leases. So it's a similar, in this particular case, for research purposes, if you want to put something in those waters, you would just go to the BOEM and say, hey, I want to do this research, and you can get a fairly quick turnaround on a permit if you're doing any kind of fixed structure, let's say. So, but no, since nobody's really doing that in the US, in other words, putting a tower in, I haven't seen that coming up. But for this, it has to go through an entire permitting process for development of the offshore wind energy areas for an offshore wind farm. And that takes about 3 to 5 years.
So what Jeff's talking about, there are three zones. There's 3 miles of New York State or New Jersey State. 12 miles is the territorial limit of the United States, but out to 200 miles is what's called the exclusive economic zone, which is part of the United Nations law of the sea. So although international shipping can travel unhindered in that EEZ, the extraction of resources from the water, the fishing, or the bottom, in this case, wind energy, is still under the control of the United States. Have I got that right, Jeff?
Yes, yes. So, everything from fisheries, mineral extraction, now renewable energy extraction is going to be under the U.S. jurisdiction.
Want to ask questions, students?
Jeff, this is Jack McSween. I'm sorry, I can't do video right now, but I just had a question about, you mentioned with Ambrose, the issues related to birds being attracted to the platform. And I'm
Yes.
curious what what did you guys learn from that, and how is that impacting sort of designs that you'd be planning for the future?
For research or for wind turbines?
For research stations.
Yeah, well, don't use a sonar out in the ocean. That's the first thing we learned. We did actually, back then, LiDAR wasn't a technology that was generally available for this kind of application. Sonar was certainly cheaper. But what we learned is I had two problems out there. One was the acoustical interference from the tower itself, when the wind and waves, wind blowing through the tower and waves hitting the tower. So that was an issue. It wasn't a major issue, but yeah, if you're putting something on a tower, birds are going to be naturally attracted to it. It's a place, to rest, essentially, and if you're a bird, just to chill out. And we tried different approaches in terms of we saw what was happening, and we tried different approaches in terms of trying to prevent birds from sitting on it, putting up wires and things like that. But birds are very clever. Now LiDAR, so to me that the future is now, in terms of measurements out there, is buoy-based LiDAR systems. You don't necessarily get that kind of perching. The LiDARs are much more impervious to issues involving birds, unless something happens, where the window where the LiDAR is transmitting, the laser is transmitting through. But that gets cleaned, so you have a little windshield wiper that takes care of that. So
It's
yeah,
1 o'clock.
So your buoy-based LiDAR systems are going to be used for resource assessment and monitoring out in these waters, and for science applications. And again, we're developing a flux system too to go on one of these buoy-based LiDAR systems. So I think for scientific research, you now have a nice platform for this kind of work. And I know we're working with DOE, Pacific Northwest National Lab, and others in developing these full systems that can study everything from, what the wind resource is from the sea surface above to what's going on below the surface as well. And there's also, you have to do monitoring for birds, mammals, marine mammals, etc. And I think these are really good platforms for that.
Anybody? Well, thank you. If anybody wants to just send a question via the chat, if you'd rather remain anonymous and you're a little shy about speaking up, just send me a chat.
Hi, my name's Christina. I'm a first-year SoMAS student here. So this is more of an opinion question, I'd say, but given that Hurricane Sandy spurred the development of the mesonet system, would you consider that kind of a silver lining compared to the widespread negative impacts that you talked about in reference to the hurricane?
Yeah, I mean, if you want to look for any kind of silver lining, it's more of a wake-up call. That having a mesonet in New York State was something that we had talked about here for years prior to Sandy and Irene. It was something that we were looking to model after. Oklahoma has a mesonet. And that was basically surface stations, just giving it, because in New York State, you only have, those National Weather Service stations. I've mentioned ASOS, that stands for the Automated Surface Observation System. So those are the weather that you get from the airports, Kennedy Airport, LaGuardia Airport, Islip, Farmingdale on Long Island, and the exception being New York City and Central Park. Most of these are at airports. There's 27 of them, 27 throughout the state, and they're only giving you those surface measurements. So it's not covering the entire geographic diversity and climatological diversity that you have in New York State. And airports tend to be located, where? At low places, open places. So this did spur that on because we wanted, we were not getting sufficient coverage. We were getting, terrible floods in upstate New York, the Sandy damage that you had downstate. And, most of the power outages from Sandy were still wind related, not tidal related. And so we needed better reporting, we needed better observations. And then we decided, hey, you know what, let's put profilers out there. Let's put wind profilers and microwave radiometers, which gives you temperature and humidity profiles. And so, Sandy coming along and then the supplemental funding available from Sandy through appropriations, we were able to get $30 million to deploy, purchase all that instruments, identify all the sites and deploy everything. Now we have to have an operating budget. So if you think of a network of any kind of network like this, observation network, roughly a rule of thumb is 10% of your cost for deploying is going to be your annual operating budget. So that's something that we're working on now, needing that $3 to $4 million a year to operate it. We do get support from the feds, but yes, this was definitely something that has helped. The National Weather Service forecast offices in New York State have been very happy with it and have been taking advantage of it. Emergency management folks at the local level use this data all the time. So in that sense, it was a silver lining.
You have a big advantage though over we oceanographers in that setting up monitoring stations in the ocean is extremely complicated, extremely expensive, and we can't possibly hope to have the kind of marvelous network that you folks have been able to put throughout the state. Now, what happens? I mean, these storms don't respect political boundaries. So what about neighboring states like Pennsylvania and Connecticut, et cetera? Are they have similar initiatives to set up their own networks?
Well, you do have, New Jersey has a mesonet, but again, it's just surface stations. New England, there are additional stations as part of different networks, amateur operating networks, but there's nothing like this. This is first order climate kind of stations plus the profilers. There's nothing like this actually on the planet. We have had conversations with the other states, especially New Jersey and Connecticut, about expanding the network. Actually, this came up yesterday during one of our science meetings. And the NOAA does have this call for a nationwide network of profilers. So there is funding for something like that, but we have a long ways to go. And one thing I would point out is that you have the ocean, and as you know, it's a real data sparse region. And what would be nice is if we can, I've been thinking of like, it would be nice to get these buoy-based LiDAR systems permanently stationed in several places. And so I've had talks with various entities about doing something like that. The idea would be to collaborate on that, via multi-institutional collaboration to do something. I think it's really necessary to have these kinds of observations. So there is talk, there is some activity, but nothing of any consequences come of it. I'm hoping that we can move that along before the next horrible disaster comes along. It seems to be we're kind of reactive rather than proactive.
Well, that is a very important cultural comment to make at the end of your talk. So I think we better shut it off, Jeff. Maybe you could just stay on the line if you want to chat with a few folks, but thank you for this fascinating talk. I just hope we don't have any ship collisions with these multitude of wind turbines, like the way that Ambrose Navigation Tower was knocked over. But I think
Yeah.
GPS is much easier to navigate more accurately these days, I think.
Yeah, I mean, they were very careful at BOEM in terms of laying out, exclusion zones where you can't put these. And those exclusion zones, of course, include shipping channels and navigation channels and other things as well. And there's been a lot of involvement with the fisheries folks. So, you just hope for the best, but so far so good. And Europe has a long experience with this anyway, so.
Yes. Well, thank you very much, Jeff, and let's all thank Jeff for the time and trouble he came at short notice to give us this presentation. So we look forward to seeing you soon. Bye for now.
Okay. All right. Thank you all.
Hi, I have a question. Is that okay?
Sure, go ahead, Ian.
Sure, go ahead. Still here?
I was wondering, so I believe you said that the ECMWF predicted the trajectory of Hurricane Sandy really well, but several American organizations just thought it was just going to go into the sea. I was wondering, is there a certain reason as to why this is a European organization, I believe you said? Is there a reason as to why they were correct?
So, I mean, I can do some speculation based upon, what's in the literature, talking with other people. Back then, the DFS, that's the American model, did pick up on that left turn a couple of days later. So, 72 hours out, it did say, yeah, this is going to happen. Why the ECMWF was superior on that is, some people point to better data assimilation approaches that they have. The Europeans tend to be more concerned with these large storms that come in from the Atlantic onto the continent. So they're more concerned about the medium range in terms of forecasting skill. In the US, the emphasis had been on mostly the short-term stuff, convective storms, things like that. That's why they developed those short-term models, got a lot of attention, such as the high resolution rapid refresh or the HER. I think today you can make the argument that the GFS and the ACMWF model skills, that gap is closed. And so, but yeah, that's from what I've heard, it's more of a data assimilation approach than anything else. And everything starts in modeling and forecast with data assimilation.
So Ian, just share with Jeff and myself. You're a new student, you've been here for some time. What degree are you taking and who's your advisor?
I just got here. I'm a first year SoMAS student. I'm an MS student and I'm studying seabird ecology. So this isn't really my realm, but still very interesting.
Okay.
Yeah.
Oh, thanks for sharing.
Yeah, thank you. Thank you for the presentation.
You're welcome.
You still there, Emma?
What's
No.
that? Sorry.
No, I'm just talking. There was another person still on the line that might have wanted to ask a question. Well, that was great, Jeff. Oh, hello. You have to turn the camera. I have to turn the microphone on.
Hi, everybody.
Oh, this is the classroom. This is where you would have been in a normal world.
Okay. Yes.
This is our seminar room.
Mhm.
You've been there, I'm sure. So, yeah. Thank you.
I think, yeah, in 2018 when I came down, when we talked, I think.
Oh, that was great. I mean, you pitched that just at the right level. And so it's just, we have a lot of new students and worry about the marine sciences, getting some of the fundamentals of physical oceanography across, and I'm always preaching that, you can't understand the biology, the fisheries, the water quality, the weather, unless you study the physical oceanography and the forces that move water around and create waves and erosion and all the rest of it. So yeah, so that was great.
Thanks. Yeah. No, understanding the physics is really important, getting down to those basics.
Yeah.
Because if you have an understanding of that, you can kind of understand everything else that's going on, or at least.
And I think yes, you really are unique, aren't you, about having you're a practicing attorney as well. I don't know anybody in oceanography who has that kind of skill.
Yeah, I think I'm aware of one other person that was an attorney that went my route. I think he was at either NCAR or out in University of Washington for a while. So I did run into him, but that's about it. I don't know anybody else who did what I did, which was a little crazy.
Okay, well, let's keep in touch. And
Yes,
if you are interested sometime this semester in making a presentation to a little physical oceanography discussion group, let me know.
will do.
And
You're gonna be, yeah, go ahead.
yeah, I'm around.
I'm gonna be down for that Advanced Energy Conference in New York City starting on the 7th. I'm not sure if you're gonna go out there. It's gonna be in Midtown Manhattan. It's the 7th, 8th, and 9th. But so I'm on a panel on the afternoon of the 7th, and I figured I'd hang out for the conference on the 8th.
Oh, you should. I'm not sure I can make it, but
Okay. And then on the University of Delaware is hosting the North American Wind Energy Academy in Newark, I think on September 18th.
what does that word academy mean?
It was something that was set up years ago by some folks. It's kind of funny to me, but it's sort of a consortium of universities and others to essentially support wind energy in North America.
Talking about the University of Delaware, the president used to be the provost of Stony Brook,
Oh, okay.
and he's a Greek guy. I'm trying to think of his name, but he actually is a mechanical engineer by training,
Mhm.
and especially in trying to develop high efficiency gasoline engines, which I guess is a past skill, but I can't remember his name, but at least he understands science and engineering. Okay, I'll let you go, Jeff, and thanks very much, and hopefully we get something going about Roma shoals, and I'll keep in touch with Keith and so forth.
Will do. Sounds great.
And we record it, so we also have a website, a sort of, can we put this talk on the website?
Okay.
It's called metrosurge.org, and it's just to do with everything related to storm surges and Sandy, and it's trying to get the word out to the public and keep this whole thing alive.
Yeah, I mean, it's, people kind of like time, time essentially kind of like minimizes, well, it just diminishes people's memories in terms of.
It sure does, and people shrug the shoulders, say, well, 10 years, it was a freak of nature. We can't afford to spend millions and billions of dollars in protection, and just turn their back on the problem.
I point out to people that New York City and Central Park had, within a week, back-to-back 100-year rainfall events.
No.
And I said, well, it's a real misnomer when you talk about those. Low probability events don't necessarily mean they only happen at a certain frequency, and especially when you have a climate system that's being perturbed constantly with climate change. It's
You might say I was just extraordinarily flukishly lucky when I predicted that New York City was going to get hit.
Yeah.
And it was 7 years. Now, if it's one in a 700-year event, the probability of my being believable is pretty tiny as well.
yeah.
But I think that ignoring the tidal range and the timing of a hurricane, maybe not so important for a winter nor'easter that lasts a long time. It's critical. So people say, well, doesn't that reduce the probability? I say, well, no, we get a spring tide every 2 weeks.
Yeah.
And
you get high tides twice a day.
yeah, exactly. And it's interesting with you talk about your cousin in the city of Long Beach. We've been doing some research on the Great South Bay, and our modeling using Sandy reformulated wind shows that much of the damage in the city was due to internal wind stress along the axis of Great South Bay, like having a northeasterly wind just piling water up the western end.
Yes.
And it was even more dangerous than the surge from the ocean. So the community was battered both from the ocean side and the Back Bay side.
Yeah, and I think that had to do with the fact that the western end of Long Beach was hit much harder than the east end of Long Beach.
Is that
Yeah.
right? So
Yeah.
there was a gradient water level even over that short distance.
Yeah, my cousin had, he had a friend of his was actually practically trapped in the basement on the west side of Long Beach because the water was level, for some reason, was a little higher. And back there, that's where the water was coming in through people's basements because of the backups on the sewer. So on the storm drains and sewers. So there were some serious problems there where people almost didn't get out alive.
So I'm just working on a report now where we've come up with a system of, in addition to conceptually looking at sea gates at the 6 tidal inlets on the south shore,
Mhm.
if we put transverse baffles within Great South Bay, 3 or 4 spaced east-west, to
Mhm.
kind of stop the sloshing around, we can actually kind of prevented Long Beach being flooded at all, believe it or not.
Yeah, no, really.
So that's an interesting, and that's not a new concept. I mean, your baffles inside aircraft wing fuel tanks and gasoline tankers on the highways and ships carrying liquids and just trying to constrain the actual movement.
Yeah, no.
My dentist in Stony Brook, he has a second office in Long Beach, and it was on the ground floor of a 2-storied house, and his whole practice was destroyed.
Mm.
And FEMA only would accept claims from private residences, so we got nothing in insurance.
Wow.
So I wiped him out for a few years. I think he's back in business.
Okay.
Okay, well, I'll let you go, Jeff, and thanks very much.
All right, Malcolm.
We'll talk soon.
We'll definitely talk soon. Thanks a lot.
Okay, thank you. Bye-bye.
Bye-bye.